Section 2.6 Limits involving infinity, asymptotes of graphs. This is a continuation of what we did on Monday and Wednesday. Horizontal asymptotes. By definition, a horizontal asymptote y equal to b, or rather a line y equal to b, is a horizontal asymptote of the graph of y equal to f of x if either the limit of the function as x approaches plus infinity is b, or the limit of the function as x approaches minus infinity is b. And here we have these two examples which I've already talked about in class, where here the horizontal asymptote of this graph is the line y equal to 5/3. Okay, and notice how the graph approaches the horizontal line as x approaches plus infinity or as x approaches minus infinity. In this other, the one on the right, this graph on the right, the horizontal asymptote of this graph, as we can see, is the x-axis, which corresponds to the line y equal to 0. When is the horizontal asymptote 0? Like from this previous slide, we had an example there. Let me go ahead and give you an example where we can find the horizontal asymptote. Have y is equal to x plus 1 over x cubed. If I divide both the top and bottom by the highest occurring power of the x, it'll be the same as multiplying both the top and the bottom by 1 over x cubed, 1 over x cubed, and so this becomes 1 over x squared plus 1 over x cubed over 1. And we recall that the limit of 1 over x to a power, a positive power, as x approaches infinity is 0, so this all goes to 0. So the limit of y as x approaches infinity is 0, which gives us a horizontal asymptote of y equal to 0. Okay, so when is the horizontal asymptote 0? Again, when the degree of the numerator is less than the degree of the denominator. Now, when is the horizontal asymptote non-zero? Let's take an example. Y equal to 2x squared plus 4x divided by 3x squared plus 1. And again, we divide both the top and the bottom by the highest power that occurs in the rational function here, and it's 2. So divide everything. That would give us 2. That would give us 4 over x. In the denominator, it'll give us, here it'll be 3 plus 1 over x squared. And when we let our x's approach infinity, these terms go to 0, and we are left with a constant 2/3. So the limit of y as x approaches infinity is equal to 2/3. And this is, in fact, our horizontal asymptote would be y equal to 2/3. And when is the horizontal asymptote non-zero? When the degree of the numerator and the denominator are equal to each other. Okay. Oblique asymptotes. Find the oblique asymptote of the function y is equal to x squared plus 1, whole thing divided by x minus 1. So when does an oblique asymptote occur? And in this case, when the degree of the numerator is just 1 greater than that of the denominator. And we will see why that is the case by performing long division on this rational function. So x squared plus 1 divided by x minus 1. That will be equal to x squared divided by x is x. Multiply through, you get x squared minus x. Subtract x squared plus 1 minus the whole thing x squared minus x. That takes away the x squared. And 0x on the top minus x minus a negative x gives us x, and then you drop down the 1. Remember that there is a middle term here whose coefficient is 0 for 0x. That's how we get 0x minus a negative x, we get x. Then you drop the 1 down. Now x divided by x is 1. We'll put 1 there. And multiply through, you get x minus 1. Take the difference again, and we have 1 minus a negative 1 is 2. And this is your remainder term. And so another way of writing y would be x plus 1 plus the remainder 2 over x minus 1. And this linear term that we got out of our long division is your oblique asymptote, or our slanted line. It is a linear function with slope 1 and y-intercept 1. So it's this line y equal to x plus 1. So there's your y-intercept 1 there. What does this mean? If I get my x large enough, this term goes to 0. Okay? So what happens is that this graph will approach this oblique line. So it'll be approaching in this manner. So as x gets large, this curve here will approach the oblique asymptote right there. Okay. Now how did I know to graph it here and to graph it there? Well, there'll be a reason when we complete the graph, and that's, in order to do that, we'll have to find the vertical asymptote, if any. Okay. Definition. A line x equal to a is a vertical asymptote of the graph of a function y equal to f of x if either the limit of the function as x approaches a, that same a here, coming from the right is plus or minus infinity, or the limit of the function as x approaches a coming from the left is plus or minus infinity. And what we've got here in this, if we examine our y equal to 1 over x, notice that the denominator will be 0 when x is 0. So we'll have to find out, is this a vertical asymptote? So we take the limit of 1 over x as x approaches 0 coming from the right. If I approach 0 coming from the right, these numbers will be very, very small. They're positively small numbers. So if we take the reciprocal, it'll be plus infinity. If I take the limit of 1 over x as x approaches 0 coming from the left, so I'll take on values, I'll try values that will approach 0 from the left, say negative 0.1, negative 0.01, negative 0.001, and when you take those reciprocals, they become very, very negative numbers, so that the limit of this ratio is minus infinity. And look at the vertical asymptote, indeed, is the y-axis, which is the vertical line x equal to 0. The curve approaches the vertical asymptote. Alright, let's look at the previous example. Graph the following, graph the function by finding the vertical, horizontal, or oblique asymptotes. Okay, remember that we performed long division and we got this, and we said that this is the oblique asymptote, which is the line y is equal to x plus 1. Okay, now to get the vertical asymptote, we find the x which makes the denominator 0, and in this particular case it's when x is equal to 1. And then we try to evaluate the limit of the rational function as x approaches 1 from the right and from the left. When we approach, well, let's examine this. What do we mean by x minus 1 and x is coming from the right? That means I will plug in numbers close to 1 from the right. It would be, say, 1.1, 1.01, etc. What happens is this number will approach 0, but they are all positive numbers. getting closer to 0. And this is just 1 or some number close to 1. When you square it, this number will be close to 2. So a positive divided by a very, very, very small number that's positive will give us plus infinity. Now, on the other hand, if we evaluate the limit of this ratio as x approaches 1 coming from the left, what would be numbers that we can approach 1 from the left? Say 0.9, 0.99, 0.999, etc. On the top, it remains positive because you square that, it's close to 1, and 1 squared plus 1 is 2. And then, but on the bottom, or in the denominator, when we take the difference between numbers that are close to 1 from the left, this is going to be very, very negative numbers close to 0, so that the reciprocal will be approaching minus infinity. So what can we conclude now? We can say that x equal to 1 is a vertical asymptote, because the limit of the function as x approaches 1 from the right, from the left. From the right, the limit is plus infinity. From the left, the limit is minus infinity. Okay. Remember that in the previous slide, I was able to graph just a portion of this function. And we said that as x approaches infinity, the graph approaches this oblique asymptote. And then, if as x approaches 1, coming from the right, and you see that the limit is plus infinity, I know to draw the graph here. X approaches 1 coming from the right, you see how it goes to plus infinity, and as x approaches 1 coming from the left, this goes to minus infinity. Right there. Okay? And I just knew that this is going to cross the y-axis at -1 because I just plug x equal to 0, and when x is equal to 0, what we have is just 1 over -1, so that's -1 right there. Okay, so that is now the graph of the function y is equal to x squared plus 1 over x minus 1. Okay, so this is our vertical asymptote, and this is our oblique asymptote.